Today we're going to discuss velocity, area, and distance. Now what we're getting at is to the heart of the theory of integration. So using relatively simple arguments and observations, we're going to understand something deep about the meaning and the interpretation of the definite integral, even in advance of actually introducing the definite integral. So it starts off with a relatively simple example, one that you're all aware of. And that is as follows. So suppose I have a graph of my velocity, v of t, as a function of time. So you're all aware that the velocity is the derivative of distance. So x of t is the distance that I've traveled as a function of t. The derivative of that, x prime of t, is just equal to the velocity. So just keep that aside for the moment. So in this example, suppose we have a constant velocity. So we'll do something very simple. So suppose here we have 2 o'clock p.m. and then over here we have 5 o'clock p.m. And we have a constant velocity of 70 miles per hour between 2 and 5. Simple like that. How far did you travel? So how far did you drive? If you're driving along the highway at 70 miles per hour and you drive for 3 hours, what's your total distance? Well, it's simple. It's 210 miles. Everybody knows that we take 70 miles per hour, we multiply it by 3 hours, and we get 210 miles. So the total distance is 210 miles. Now, this very simple example actually lends itself to a very deep and profound observation, and that is the following. So the units of the vertical axis are miles per hour, and the units of the horizontal axis are hours. So time is in hours, and velocity is in miles per hour. What does 210 miles represent on this graph? So the answer is as follows. Well, it's the amount of time. So the amount of time would be 3 hours. And then the height up here is 70 miles per hour. So that 70 miles per hour represents this length. So if I multiply 3 hours by 70 miles per hour, what I'm actually figuring out is the area of the following rectangle. So if I make a rectangle, the area of that rectangle is going to be 210 miles, right? So why does area have units of miles? Well, that's because the width of it has units of hours down here on the horizontal axis, and the height has units of miles per hour. So when I multiply hours with miles per hour, I just get simply miles. So the area under this curve, or so the area underneath this line, so the area between the line and the t-axis is just 210 miles, which is the total distance that the car traveled during that period of time. So what we observe is that the distance, at least if you have a constant velocity, is simply the area under the velocity curve, as long as you have a constant velocity. So this is a very, very interesting observation, that distance can be thought of as the area under this curve. And the natural question is, well, what about if your velocity is not constant? So suppose we have velocity in miles per hour, and we have time in hours, and we have something crazy happening like that. And we have time t is equal to a, and maybe time t is equal to b. So the question would be, is the total distance that you travel still equal to the area that lies underneath this curve and above the t-axis? So does that area still give you your distance? It might seem amazing or astonishing that it would. After all, we have some random curve of your velocity. why does that correlate, or why does that area that you sweep out correspond to distance? When the units match up, hours times miles per hour is still miles. But why does this area in general give you the total distance? Well, the answer to that is as follows. Even though we have a non-constant velocity, you can still break down the interval from A to B into a bunch of small, tiny pieces. So if I'm just traveling, if I just look at how far I travel for this small interval, well, I have to look at what's happening between these two moments in time. Between these two moments in time, the function v of t only changes slightly. So it's approximately constant. I mean, think about, even if you're doing something crazy on the highway, speeding up and slowing down like that, if you only look at your velocity for between over a 1 second period of time, or over a tenth of a second period of time, a very, very short interval in time, you can figure out how far you've traveled in that second of time, because your velocity is approximately constant. You're not speeding up so much as to see a dramatic change in your velocity over 1 second, or over a tenth of a second, or as small as you need to make it. So for this small little interval, we can approximate the velocity as a constant like that, and so the area under that constant should equal the distance that you travel for that small little interval in time. And the smaller you make the interval, the more accurate it gets. So what do? Well, we can do that for all these intervals. We can basically chop this up with a bunch of small little intervals, and then each interval has a rectangle, and for that short period of time, the function is approximately constant, so the area of that rectangle is very close to the actual distance. So you can see that we can basically take this observation with constant velocity and extend it to the general case by just looking at fine enough intervals in time so that the assumption of constant velocity is valid over all these super small intervals. Well, maybe not precisely valid, but pretty close. I mean, if you look at the change in your velocity over a nanosecond, it's not going to change very much. So over that nanosecond, the distance that you travel is just equal to the area. So if you do this fine thing and you compute a bunch of little rectangles over small little intervals, you can add them up and get the total distance. So basically, the total distance traveled is equal to the area underneath the curve. So it now becomes very interesting to compute the area underneath curves. So how do we compute the area of something like this? So it seems like a complicated thing. Now, as it turns out, with calculus, computing areas under curves is relatively straightforward. If you can compute an antiderivative of your function, you can compute the area. And we'll get to that as we progress. But there's another observation, and that is that, well, we said that v of t is just the derivative of the position. Now, the total distance is going to be your position at time b minus your position at time a. So the area underneath the curve is equal to the total change in the position. So this is the total change in position, which is equal to the antiderivative of v evaluated at b minus the antiderivative of v evaluated at a. In other words, it's x of b minus x of a. And that's basically the heart of the fundamental theorem of calculus right there. And we'll get into much more depth on the fundamental theorem and what all this means in future lectures, but that's basically the essence of it. And if you understand that, you basically understand what it means. Now, there's another case that I should mention. And suppose my velocity looks like this. So sometimes my velocity is positive and sometimes it's negative. In that case, we count the area above the t-axis. Area above the t-axis is counted as positive, and then the area below the t-axis is counted as negative. And the reason is as follows. So positive velocity means that your x is increasing. So x is increasing. Negative velocity means that x is decreasing. So the area still represents the distance, except if it's below the t-axis, it's distance you've moved to the left. If it's above the t-axis, it's distance you've moved to the right. So to find the total change in your x variable, you want to compute the positive part and subtract off the part that's below the t-axis. So your total distance, x of b minus x of a, so this is, let's say, a, and then this is b, and let's call this point in between c. And let's call this one area 1, and the one down here area 2. And area 2 is the positive area, so it's just literally the area underneath the t-axis. So x of b minus x of a, the total change in my distance, or my position between a and b, is going to be a1 minus a2, because I've moved a distance of a1 to the right, and then I moved a distance a2 to the left. If I wanted to look at x of c minus x of a, that's just equal to a1. If I want to look at x of b minus x of c, that's going to be minus a2, right? So minus a2 indicates that x of b is further to the left than x of c. In other words, x of b is smaller than x of c. So I'm decreasing in x, so I get a negative distance.